So hello everyone, welcome to week 3 of this PTL course. So hopefully all of you got check your results for submitting your first two assignments. We covered details of backpropagation in this during this week, so we can discuss the problems if you have any doubts for week 1 and week 2 assignments, or we can practice some problems for clearing the details of backpropagation. So let me connect to my iPad, and meanwhile you can unmute yourself and ask if you have any doubts, or you can type your doubts in the chat. Okay, so let us hello. Yeah, is my screen visible? So first of all, are there any doubts because you got the solutions for week 1 and week 2 assignments, right? Do you have any doubts in those assignments? Is there any question that you may need to discuss? Okay, so if there are no doubts, then maybe we can discuss about feed forward and back propagation algorithms that were covered in the class, right? So as an example, let me take one, and I want you to answer if you can, because this will help you solve the questions during for this week. So suppose we have so this is your input layer. You have your x1, x2, x3, and x4. You have 5 here. Say, so I am dividing this as activation 1 and pre-activation 1, pre-activation 1 and activation 1. And I connect it to, say, so these are your layer 1 activations and pre-activations. Now I have your layer 2 activations. And suppose I'm taking suppose we have a classification problem, right? So now these are all connected. So I will not show all of the connections. So these are connected somehow. So yeah. So I want. Can anyone answer what is the number? So now I am saying that this is a classification problem. So what is the number of classes in this that this neural network will be trained for? Anyone? You can type it in the chat or you can unmute yourself.
Two, sir.
Yes, hello.
Two classes,
So
sir.
two classes, right? So because we are doing a classification problem and our output will be a vector of length 2, so we'll need two output dimensions here, right? So now we'll have the weight. So for now, say that the biases are not there. We're just considering the weight. So we have the layer 1 weights and we have the layer 2 weights. Layer 2 weights. So now what is our input dimension here? What is the input dimension that you have? So this is our input layer. What is the input dimension that you have? Yes, right, 4. Thank you, Ishaz. And how many? So now we have 4 layers or 4 as the input dimension, and we have 5 neurons in the hidden layer. So what should be the size or what should be the dimension of this weight matrix? 5 by 4, right? So is it clear why is it 5 by 4? No. So I'm asking about the dimension of the weight matrix. So when I say dimension, so this will be a matrix, right? So I'm by dimension I mean what is with the number of rows and what will be the number of columns. But as Isaz, you were saying that 2020 is the number of parameters. So there will be connection from here to here. So each of these connection represent a parameter. So yeah, 20 is the number of parameters and dimensions is 5 by 4, right? Okay, good. So once we have this, so now earlier we had your, suppose I am writing X is the collection of say X1, X2, X3 and X4, and now I apply W1 on this, W1 of X. So W1 of X where W1 is 5 by 4. So your, what will be this size? What will be the size of this vector? So Gurava, if I am spelling your name correctly, do you understand why this is 5 by 4 and not 5 by 5? Okay, so I'll first show you why this is 5 by 4. So first of all, suppose you have an m cross n matrix. So m cross n means your number of rows is m, your number of columns is n, right? And if I multiply an m cross n matrix with an n-dimensional vector, so this is an n-dimensional vector. So what will be the size of the output? Kuraba, you can answer. Yeah, so it will be an m cross 1, right? No. If we multiply an m cross n matrix with an n cross 1 vector, our output will be an m cross 1 vector. So how do you get this? So you have this n rows here, right? N columns here, and you have this n rows in this vector. So each of these will multiply this plus this into this plus this into this. So all of this n, so this row will multiply with this column and give us one number, right? So it will give us the first entry, this and this. The second row with this column will give us the second entry. So in this way, how many sums will have? We have m such sums. So we'll have m as the output dimension. So is this clear? How you're getting an m cross 1 by multiplying m cross n and n cross 1? Okay, good. So now, so what is the so what is the logic behind having this as 5 cross 4? So we have this four-dimensional vector, and now I want to move it to a 5 dimension because we have 5 hidden neurons in this case. So I need to multiply a 5 by 4 matrix. So I have a 5 by 4 matrix, and if I multiply it with say 4 cross 1 matrix, I will get a 5 cross 1 matrix. Is this clear? So what will be the first of all? Yeah. So before going, so what will be the entries of this weight matrix? So I am drawing this. So I am copying this part. So we have this part, right? And now let us forget about all this. So now this is 1 with 1. So I will say this is W11, W12, W13. This is W14, and this is W15. Similarly, this is W21, W22, and so on. So now you see that if I place each of these connections into an entry, so we have your W1, right? So for W1, so we have W11, which is this one, the weight of connecting input dimension 1 with the first hidden neuron, that is W11. So what is this? The weight of connecting input dimension 1 with the second hidden neuron. So that is W12. So this will be W12. Weight of connecting first input dimension with the third hidden unit. This is W13. So this will be W13. So on. And now we have W14, W15. So basically this column says that what is the weight of connecting X1. So these are your H1, H2, H3, H4, H5. So you have your input dimension in this column, and these are the neurons in the next layer that you have. And this row and this column gives what is the weight of connecting the this input dimension to this hidden neuron. This is W11. So similarly for the second input dimension, we will have W21, W2, and so on, right? We have W23. So, and finally we have 4 input dimension. We have X41, and then we have X45. So now what we get? So there are 5 rows in here, and there are 4 columns. So there will be X3. There are 4 columns. So that is how we get the 5 by 4 matrix. Is it clear how why we have a 5 by 4 matrix here? So basically, we have to do a, yes, basically we have to do a wx plus b. So for now, let's say b is 0 to make things easy, or otherwise you can just add a vector. Okay, right, good. So this one, so now we finished. So now we finished with these weights, right? Now let's try to look at this thing here. And because this is hidden layer 1, so I am saying this as h1, right? So let us look at h1. So at h1, we have a vector of length 5 cross 1, right? So for neural networks, what do you do? So at first you do wx, and what is the next step? So this is the aggregation step. So this is the aggregation step. And then you have the non-linearity step, right? So in non-linearity, you apply some sort of non-linear function on this wx, right? So this is your non-linear activation, non-linear or activation step. So that is why if you looked into if you saw the class, you'll know that for each hidden layer neuron, there is a hidden layer, or there is this aggregation step, which is this h1, and then there is this activation step. So at h1 we have this wx type of computation, then we do a sigma of this h1, to get a1, right? So now, so suppose we have this, so we have h1 at the hidden layer 1, we have h1, we have we have h2, we have h3, h4, and h5. So now we want to apply this non-linearity. So what is the dimension? So suppose I give a vector of all h. So suppose h1 is your capital H1 is your, say, h11, h12, h13, h14, h15. So suppose I have these hidden activation or pre-activations. So these are your pre-activations. So the next step we need. So how many number of how many activations are there? How many activations will be there? Suppose we have 5 pre-activations or 5 aggregations. How many pre-activations will be there? 5, right? Yeah. So we'll have 5. So that means we will have to apply a the nonlinearity on each of these vectors. So for h1, we will have sigma of, so sigma is some nonlinearity activation. It can be anything. So in the class, the professor talked about sigmoid or 10H, or there could be some other thing called as ReLU, which we covered in later class. So we have sigma h11, sigma of h12, and so on. So let us say that this is A1, this is A2, this is A3, A4, and A5, right? So now from H1, so if you want to write it in a short notation, so I will say that we have H1, we apply some non-linearity. So this is element wise, because we are applying the non-linearity on each element of this vector. So we apply element wise activation, and we get some vector, say A1. So what is your A1? A1 is your A A11, A1, A12, A13, A14, A15, right? Right. So now we have covered this, cover this part of the, network. Now let me copy this part. So now here at this point, we have this vector a1. So what is the size of a1 again? Anyone is to repeat it? So it is a vector of size 5 cross 1, right? Yeah, right. And now I want to multiply it with some weight w2. So what will be the dimension of w2? Right. So yeah, we need a 2 cross 5 matrix because we have a 5-dimensional vector here. We have 5-dimensional vector here. I want to go to a 2 dimension. So I will have a w2 which is of size 2 cross 5. So we have a matrix of size 2 cross 5. So what will be this 2 cross 5 matrix? So here I have say this is A11. So this I will say that this is W211 and this is W212. So similarly this is W221 and this is W222 and so on. So we have again we have two hidden neurons here, H21 and H22, and A11, A12, A13, A14, A15. So we have W for hidden layer 2, we have 1, 1. For hidden layer 2, we have 1, 2, and so on. So we have finally W2, W251, and W252. So we get this 2 cross 5 matrix. So what is the operation we are doing? We are doing uh, we will get some H2 hidden layer 2, which is basically W2 times your A1. So what will be the size of this H2? What will be the size of H2 here? It's simple, right? We're multiplying a 2 cross 5 and we're getting with a 5 cross 1 vector, and your H2 becomes right. We have this 2 cross 1 matrix or 2 cross 1 vector H2. And so now we get the outputs S. So yeah, so suppose we get the outputs as H2. Now it depends whether you to. So in the class there were two things that were shown. So suppose you have a multi-class classification. So this was the description of the feed forward algorithm. So whenever you are trying to implement or create a neural network, you may be using some libraries, say PyTorch or TensorFlow. So there, the main thing that is needed is you have to specify how many neurons you want in the hidden layer. So if you are using images, your input will have some input dimension. You will give some number of hidden layers, and then you have to specify what is the type of activation that you want to use and how many layers that you want. So in this case, we have only one hidden layer. So if you are designing some neural network, you will have to specify this. So getting the sizes correct is very important in that case because otherwise you'll be getting a lot of errors. So is the feed forward algorithm clear, or are there any doubts? Okay, great. So yeah, so now we're talking about the classification problem, and we saw that in the class we talked about multi-class classification. So in sorry, in earlier classes you saw that for perceptrons or multi-layer perceptrons, if you have some threshold type of problem, so you can use the sigmoid activation function, right? So suppose you have a multi-class classification. Suppose given a fruit, you want to say whether it is banana or mango or maybe what are some fruits? Maybe some oranges. So you want to classify, given I give you some data and I want you to say whether is it banana or mango or orange. So can you use a sigmoid in this case? Yeah. So can anybody speak up or explain why we cannot use us, because these are very important decisions. What type of activation you want to use in the final layer? So can anybody explain, or do you need me to explain why we cannot use sigmoid in this case? Okay, so I think, okay, let me explain. So what is the so sigmoid, or let us say logistic, don't say sigmoid. Suppose our activation is logistic function, which is basically sigma of z, the one plus e to the power minus z. So what is the range of outputs? So what is the range of output for this? What is the minimum value that this can take?
The -1 to +1.
No, sigmoid is from 0 to 1. So one you are saying -1 to +1. If you have some 10h, so for 10h your output ranges from -1 to +1. For sigmoid your output ranges from 0 to 1. Yeah. So if you have something say 0 to 1, so diagramming, if we make a plot the curve, it looks something like this. So this is your z, and this is your sigma of z. So your sigma, your logistic function looks something like this. So this is 1 and this is 0. So at 0 it is 0.5. So how do you, so sigma is basically used for thresholding type of operation. If you have some threshold, say if I say that some for something my sigma is say 0.01, which is say less than 0.5, then I say that it is a negative class. Or if I have sigma z say 0.8, which is greater than 0.5, I say that this is a positive class. So for sigma we have some threshold value. So in this case my threshold is say 0.5, and based on the threshold I can say that whether this is less than 0.5 or greater than 0.5, and then we can have two classes, zero positive minus minus the negative class or the positive class. So here, so if I have something, some probability on this line, we have say negative class, and we have something here, we'll say that it is a positive class. Now, now if we have a multi-class classification, So this is a two-class classification, right? We have two classes. This is a binary classification, right? Positive or negative. But here we don't have a binary classification. We have three things, right? So we cannot have a thresholding type of operation like this, right? So we cannot say that if our probability is, so actually there is a way to do this. Can someone say, can we use this? Can we use this positive and negative to for multi-class classification also? So that is not wrong actually, but it is not that efficient. So can do you have any idea how we can do that? Let us give an positive or negative classes, and then using this you want to classify into say three classes. Okay, so let me show you. So suppose your data looks like this, right? Suppose your bananas are here, your mangoes are here. So my drawing is not that good, but let us say these are here, and your oranges are here, right? So now I say that suppose I have a decision boundary like this. Let me draw it. So decision boundary like this. So suppose I say that this is negative and this is positive. So according to this decision boundary, I can say that if it is positive, it is of class, it belongs to the, it is a banana, or if it is a negative class, I say that it is not a banana. So you can answer things like, uh, is it uh, is it a banana? Yes or no. So if I say that this is a positive class, this is a negative class, so then you can use the sigmoid ones here. So similarly, you will draw other lines, right? So you will next time you will say that I draw another line, and according to this line, if it is positive, then we'll have mango. If it is negative, we'll have oranges or banana. So you will use a different sigmoid here and say that whether it is a mango or not. So if it is some binary type of thing, so if you have only two classes, you can use the sigmoid. But even if you have multiple classes, if you have multiple classes and you want to do this in a binary way, so you have to do at least six comparisons, right? So you have to draw a line between these each of these. You have to do six computations and then see whether it is a banana or not. Is it a mango or not? Is it an orange or not? So that is not efficient because you have to learn each of these six decision boundaries. You have to train six of these models, right? So what we do, we use something called a softmax activation. So what it does is, so suppose you have some, so I am saying that you have classes y1, y2, or let us say you have the labels, the true labels. L is say L1, L2, L3. Suppose your L1 is your banana, this is your mango, and this is your uh, orange, right? So earlier, what you are trying to say when you are using sigmoid, you are trying to say that what is the probability. So we are saying what is the probability that my result is greater than 0.5. So sigmoid answers this question: what is the probability that your class is positive, or this is positive? So sigmoid answers this question. So if I draw the probabilities, so suppose you have negative class here and positive class here. So suppose for a data, I say that probability for this is say 0.8, and probability of the class belonging to a negative 0.2. So it can either be this, or it can either be this or this. So based on this, you can say that this belongs to the positive class, because it has a very high probability of belonging to the positive class. Now we want the same thing here. So suppose I have a probability distribution. So this is your probability of belonging to L1. This is probability of belonging to L2. This is L3. And suppose I have some probabilities like this. So suppose I have say 0.4, 0.5, and say 0.1. So for some x, your probabilities are like this. So in this case, what do you think what is the level of x in this case? What is y in this case, for this example?
Aryan, switch on the video.
Yeah, so is my question clear? So I have given you a data point x, and so earlier you were saying that we get the probability of that class being positive and negative. So because that class being positive was say 0.8, we say that the class is positive. Now suppose by some function, I say that the probability of your x being having level L1 is 0.4, probability of it having L2 is 0.5, probability of being L3 is 0.1. So according to you, what should be the class of that class, or what should be the prediction of that x point x? Yes, L2, right? So why did you say L2? Because it has the highest probability. So whenever you are trying to learn a model, what we are trying to do is, suppose your two levels are this one, and suppose your predictions are something like this. Say it is some y1, y2, and y3. So whenever you are trying to learn, you are trying to minimize this loss, right? You're trying to minimize the loss between the prediction and the true level, right? So if you want to minimize this, so you want to minimize this, right? So if you want to minimize this, you want to make the probability distributions between prediction and L to be similar, right? The probability distribution for prediction and L must be close.
Harish Sharma sir. Harish Sharma sir, please mute your mic.
So is there a question? Okay, let me do that. Yeah, so yeah. So if you have some predictions, say y1, y2, y3, and this is some probability distribution. So these are your probabilities, and you know your true probability. So we know that some object belongs to class L2. So the probability of that object belonging to L1 is 0, probability of belonging to L2 is 1, and probability of that belonging to L3 is 0, right? And now you predict something, and you want these probabilities to be close to, you want something close to this, right? This and this. But you don't have, you have something y1, y2, and y3, which is not here in this case right now. We want something like this. So when you are training a neural network, again, if I design a neural network, what is the output dimension? Quick question. If I have a neural network, what is the output dimension here? What will be the number of output neurons?
So 3, since there are 3 classes.
Yeah, right. Yeah, so you have some X here, you have some neural network. So inside there are some hidden layers, and I'm not showing all of this. And on the output layer, you have say our neuron 1, neuron 2, neuron 3. These are your output neurons, right? So this gives you some Y1, Y2, Y3, and because you want to have this type of distribution, your true label is truth values are. So you have this probability distribution, and you want to minimize this gap. So that means whatever probability you give, so at during the first feed forward algorithm, you will get some y values, then you will do some back propagation, and then you will learn some weights, and then the second algorithm will again learn give some y values. Then you repeat these steps. So what we want to do is, so given this y1, y2, y3, you want to increase the probability of y2 because you want it to be close to 1, and you want to decrease the probabilities of y1 and y3. So is this step clear? This is what the neural network will try to do. It will try to increase your probabilities for y2, and it will try to decrease your probabilities for y3. That's clear, right? So now, so if we look at the last layer, so what happens? We have some hidden or pre-activations here, pre-activations or the aggregations, right? Which are your, say I'm naming it, since this is the output here, I'm naming it as out. So you have some h1, h out 1, h out 2, and h out 3. And then as we do with any neural network, what we do, we because this is a classification function, we use the non-linearity here. We have some sigma of h out, and it will give us, say, sigma 1, sigma 2, and sigma 3, right? So what I want because we are trying to learn this distribution, we want sigma 2 to be in, we want sigma 2 to increase, and we want sigma 1 and sigma 2 to sigma 3 to decrease, right? So the activation, so earlier you saw sigma activation. So the activation that helps us do this is a softmax activation. So what is the softmax activation? The softmax activation is basically sigma of zi e to the zi, right? 1 plus or summation 1 plus e to the zi. Sorry, by summation zi or zc. So is this clear? Uh, what is the role of the this one softmax activation.
Sir, which loss function we will use?
So we'll come to that. So first of all, I'm just talking about the feed forward algorithm now. So so first of all, is this clear? Be clear. Because we want a distribution over each of the three classes, so we'll use this softmax activation. Right. Now the next question: what is the loss function? Because whenever you are designing a neural network, these are the important things to keep in mind. What are the type of, what are the size of your hidden layers? What are the activations you'll use? What is the activation that we'll use on the last layer? And the next question that comes is a loss function. So before that, this is the softmax, and is the motivation behind using softmax here. Okay, it seems there are no more questions. Okay. So now coming to loss functions. So we want, so this is our two labels, say L1, L2, L3, and we have your, so I will name this as sigma 1, sigma 2, sigma 3. And we want these two to be very close to each other, right? So a simple loss function, if you don't want to get too much into details, is you can just say that your loss. Oh, okay. Let us say that our loss function is something. This is our loss function. So J is basically, so given two things. Say this is your sigma vector and this is your L vector. Your sigma and L is sigma minus L whole square, and say 1 by 3 of this. So that is basically sigma 1 minus L1. So I do a summation of this. So this is a very simple loss function that I'm saying. So this is your mean squared error loss. So we have sigma 1 minus L1 square. We have sigma 2 minus L2 square. And we have sigma 3 minus L3 square. And then you sum over all of this. So that means you will have 1 by 3 sigma 1 minus L1 square plus minus L2 square plus 3 minus 3 square. So this is a very simple loss function that you can use. So can anyone tell why we are squaring it? So is my audio low? Okay, let me check. Is my audio clear now? Hello.
Yes.
Okay. Okay. So can anyone say tell why am I squaring this? I can just say sigma 1 minus L1 plus sigma 2 minus L2 without. Yes. So because squaring it can makes the all of these errors positive. We do not want negative error, right? So negative error means you are giving something which is better than the truth, which is not possible. So that is why we want these errors to be positive. Yeah. So this is one loss function that you can use for MSC. But we have something else. We know that this is a probability distribution, right? That summation L1 plus L2 plus L3 is 1 because it is a probability distribution. So we can also say that sigma 1 plus sigma 2 plus sigma 3 is 1. We have this. So if we do this, if we just do this computation, so we may get some sigma 1 which is very large, sigma 2 which is very large, which is not feasible or which is not efficient. because it will take a lot of time to decrease sigma to say to come to value somewhere near to L2. So we don't want that. So in this case, we use the cross entropy loss, which was covered in the lecture. So cross entropy loss basically is given by, so uh, you have this probability of class 1 being L1. So suppose I say that we have this as a true distribution. We want to learn a distribution like this, and we are given something say sigma 1, sigma 2, and sigma 3. So here, what is the probability of having sigma 1? So we have probability of having sigma 1 is 0. Sorry, the cross entropy loss is, what is the probability of getting sigma 1 and log of sigma 1. So plus probability of getting sigma L2 is 1, and the probability of getting this is log sigma 2. Probability of getting L3 is 0, and your output is log sigma 3. So this is your loss for sigma and L. Yes, L. So now because we know what our true class is, our true class is this L2, and we know that the probability we want this to be 1, and these twos are 0, so we can, these are anyway 0, so we can just continue, or we can just concentrate on this quantity, right? So now this is your loss function. So is this clear? What is the meaning of this loss function? How we can, how, what is the definition of cross entropy loss? Why is it useful? Right, if there are no more questions, good. So now if you're given a loss function, what is your task? Your task is to minimize the loss, right? You want to minimize your loss function. So minimize over what? So whenever you're minimizing a function, you have to have certain parameters. So again, what are the parameters of the network? What are the parameters of the network? Anyone? Because you will be minimizing this by changing some variables, right? Yes, right. So here parameters are your weights and biases. So in this case, we had in the example that you were discussing, we don't have any biases here. So now our parameters are the weight matrix for layer 1 and the weight matrix for layer 2. These are the parameters that we have. So suppose I say that we have some vector or matrix set theta, which is a set of all of these parameters w1 and w2. So now what I want to do is I want to change this w1 or w2. I want to learn this w1 and w2 such that your j sigma l decreases. We want to minimize this. So I say that minimize j and l over theta. So if you solve this problem, you will learn some w1 and w2, and this theta will be minimized. Sorry, this j loss will be minimized. Look at this thing. It is so there is an interesting thing to see here. So you have a negative quantity which you want to minimize. So if I reverse the sign, so if I say that instead of minimizing this, can I also say I want to maximize minus of j of sigma? So are these two equal or equivalent? So if I minimize a negative quantity, and can I say that it is same as maximizing the negative of this negative quantity? No, it is not the reciprocal. I'm just saying that I have a, so this thing is minus 1 times log of sigma 2. So the negative of this is basically just 1 times log of sigma 2, just the negative of this. So if I minimize this, minimize the negative of this, can I also say that it is, we can maximize the negative of this? So minimizing this is the same as the maximizing this. Is that clear? Hmm, right. So now we can just say that you want to minimize this, or you can do to we can maximize this quantity. So if any one of you have taken the machine learning course or some statistic course, you must have heard about this maximum likelihood estimator. So this corresponds to that. So if you're not familiar with it, there is no problem. This is just a connection to the ML. So we have defined the neural network. We looked at your sizes of weights and biases, or we are not using biases, sizes of the weight matrices, and then we define the loss function, right? Now, one thing. So this was a multi-class classification. So suppose we have a regression problem, right? Suppose you have a regression problem. What will be the output dimension be? So what will be the output dimension, or what will be the number of neurons in the output layer? Yes, in general it is one. So in general we will have one output neuron, but there are also problems when there can be more than one value for output for regression. But for the simplicity's case, let's say we have one. So if you are doing regression, what will be the activation in the final layer? Yes, linear. That is, we don't need to add any. We don't need to add any nonlinear activation or sigma. We can just have wx plus b in the final layer. And what is some loss function we can use there? Yeah. So we could also use MAC for the multi-class classification case, but we have this added information that our outputs are bounded. The output values, summing of the output values cannot be one. But for regression, there is no such bound on the range of the output values. It can be any real number. So we can use a MSC loss for this. Now, we have defined their loss. So now what is the next step? So I give you some data. You train your favorite neural network on the data and you get some output. Once you get the output, you calculate your loss. Now what should be the next step? No, we'll not go to testing yet. Yeah. So you have some input. You run your feed forward algorithm on the network. You get some output, and you also have some true labels. So using the output and the true labels, we calculate the loss. So yeah, if your loss is say 0, that is in the first step itself, your output is equal to the true labels, then yes, we don't need to do anything else. We can just use this feed forward model to test, because we don't need to change anything else. But life is not so easy, so your loss is never 0 in your first iteration. So you will need to change your feed forward network, right? You will need to change your weights and biases. So ideally or initially, your weights and biases are some random values. You do not know what is your correct weight that you want to give, what is the correct bias that you want to give. So now that we have this loss function, now I want to use this loss function to train the network, right? I have some feedback, or we have this algorithm called as backpropagation. So why backpropagation? Because you're using this loss to the correct the weights and biases of the neural network. So I think in the last lectures of last week, you saw gradient descent, right? So for gradient descent, if you have some parameters, say theta t, so at the next iteration, your theta t is minimized by some eta times some gradient of the loss at theta t. So uh, so is anyone not aware of this update step of the gradient descent? Hope everybody remembers this, because this is the most important algorithm you will need for or most important update step you will need for training your neural networks. So so in our case, we said that our theta is your set of all weights for layer 1 and layer 2. So using this update step, you will update your weights. So initially you have some random weights. So using this, you will get your new weights. So suppose I'm talking about theta 1. So initially I have theta 0. So theta 0 is basically if I randomly generate some weights and say that W10 and W20. And now at theta 0, we have so our next updated parameters will be theta 1 minus some eta and the gradient of this with respect to theta 0, right? So this is the gradient descent step or gradient update step that will update your parameters W1 and W2. So we know what is theta 0. This is some learning constant which the user can give. That is, if you give a small eta, your algorithm will learn very fast, but it may not come to a good solution. Now the most important thing is this. What is this thing? The gradient of the loss. So like we saw a few steps back, we have this loss, and we want to use this loss as a feedback for training the neural network, right? Now let us talk about this loss. So you have the loss at theta naught, and now you want to compute the gradient of this loss. So gradient is nothing, basically the partial derivative of this loss. So actually, so the partial derivative of this loss with respect to the parameters, right? Because see, in the neural network, you are changing the parameters. So those are the variables. You are changing the weights, and changing the weights will give you a different loss. So you want to see what is the rate of change of your loss with respect to the parameters. Can I get this with respect to the parameters, right? Yes, right. Rate of change of loss with respect to the weights. But let us go back to our network again. So we have two hidden neurons here, or sorry, the two output neurons here. We have, so this is our reach out. We have 5 neurons here, so reach on, and we have the input. So in this network, the inputs, so this layer will not change, right? This is constant. Your inputs will never change. So you don't need to, so there is nothing called derivative of loss with respect to x. There is nothing like this because this layer won't change. This is your input. This is constant. But this and these layers will change, right? So we'll have some loss here. So this is not a neuron actually. We have some loss. Loss is basically your J of sigma and L. Now, if we look at H out, what was H out? Any specific reason for number of hidden neurons based on number of? Okay, so we know that if we have a C class problem, if you have a multi-class classification problem, where the number of classes is say 10, we'll need 10 dimensions or 10 neurons in the output layer. But for the hidden layer, actually there is no such thing that you should always have this number of neurons. So there is this, you must have come across this term called hyperparameter tuning. So in hyperparameter tuning, what you do is you test your or you check your results with changing the number of neurons in the hidden layer or even the number of hidden layers and take whichever hidden layer gives you the minimum loss. So there is, we cannot say that this number of neurons will definitely work well for this problem. So it is a case of checking out different combinations of this number of neurons and number of layers, and then taking the model which gives the minimum loss out of all of these other combinations that you have. Is that clear? Okay, so let me give you an example. So we'll come back to this back propagation, but so suppose I have a neural network, and suppose here I have my x input. We have some hidden layer h1. I have another hidden layer h2, and I have some output layer say h out. Right. So given this x, suppose I take say 10 hidden neurons here. I take 5 neurons here, and this does not matter. Say I have some C number of classes. So your neural network looks like this. You have X, you have 10 hidden neurons here, you have 5 hidden neurons, and you have some C neurons here. So I do a feed forward of this network. I train this network using feed forward and back propagation. And suppose I get a loss of say I don't 20.5 in this case. Now I change these two things. Suppose I take say 15 and say 5 in this case. I get the loss of say 22. Now again I say I take say 100 and 200. Suppose now I get a loss of 0.5. So out of each of these three, which of these networks should I? So this is your network 1, this is your model 2, this is your model 3. Out of these three, which model should I take? Third, right? Yes. So because with so there is you must have seen the uh, before you do any training, given a data set, You always do a train, validation, and test split. So suppose I give you 100 data points. You take 70 data points for training. You take say 15 for validation and 15 for testing. So this, so you train the model with the 70 data points, right? So using this 15 validation data set, you will get these losses on the validation data set, right? You use this validation data set and get these losses. So now we see that model number 3 gives a minimum validation loss. So now you take this model and then you apply it to the third or the test data set. So this process is called hyperparameter tuning. You tune or you check out different combinations of the model and then test the best model on your test data set. Is the flow clear? Yes, it is. Yeah, mostly it depends from data. I will not say randomly, but as you work with more data, you get an intuition that this is the type of model that will work. So based on some knowledge or based on experience, you will get to know that how many hidden regions do you need to give, what is the size of the network that you want. So the general thing is that more the number of layers, better is your result. But it is mostly about intuition or experience. Uh, for that. Okay, so yes, so we are in back propagation, right? Yeah. So this was our network. We want to do update the network using gradient descent update step, and we know this quantity. We know this quantity. We do not know this quantity, and I want to compute this. So in the last layer, I have H out. I apply, so suppose I am talking about multi-class classification. I apply softmax on H out, and then I get your output layers, say Y thread. So now your loss is some J of Y thread in L. L is your optimal or the known ground truth labels that you have, ground truth probability distribution that you have, right? Now I want to compute the gradient of this J with respect to all of the parameters. So before going further, should I explain back propagation or is it clear? Is there anyone who needs who? So should I explain back propagation from scratch or is it clear to everyone? Okay, fine. So before going to back propagation, suppose uh, I give you this equation or give you this function f of x is a mm, sine of something simple. That suppose I give you this sine of x, sine of e to the x. Suppose I give you this equation and I want you to compute what is the derivative of fx with respect to x. So anyone, quickly, what is this answer?
Sine e power x into e power x.
So it's actually so okay. First of all, what we do? So we want to compute this, right? Sine of e to the x. So what we'll do? We'll first of all we will differentiate sine of e to the power x with respect to e to the power x. Okay, someone is typing. Wait.
Cos e power x.
Yes, right. Yes, right. So it is. So this is cos of e to the power x times e to the power x, right? So how did we get that? So first of all, we will differentiate sine of e to the x. Sorry for the noise. Yeah. So first of all, we will differentiate sine of e to the power x. Excuse me. Yeah. So we'll differentiate sine of e to the power x at e to the power x, and then we will differentiate e to the power x with x, right? So this will give us cos of e to the power x times this will give us e to the power x. So this was your well-known chain rule. So everybody or every one of us knows this rule. So this back propagation is something very similar. So first of all, what we did was we have this function sin x. We know that this sin x depends on this e to the power x. So that is why we differentiate sin x with respect to e to the power x, and then we go back to e to the power x. This depends only on x, so we differentiate it with d of x or with x. So similarly for the loss functions here, what is our loss function? So our loss function is a function of your y pred and L. So L is your constant. This is a true level that you have. It will not change. So this is variable, that y pred. So what is y pred? Y pred is basically the sigma of h out and L. So what should we differentiate this loss with respect to? So here we are differentiating sine of e to the power x with e to the power x. So what should we differentiate j with respect to for now? So is my question clear? What should I differ? So we saw this here, right? We differentiate it with this dependent function. So for this case, our loss depends on sigma of h out and L. What should I differentiate? So after I dj of, so what should come here? Yes. So not h exactly, because after h we also have this sigma function, right? So this j depends on sigma of h. So we'll differentiate with respect to sigma. Now, so here what we did, we differentiate with respect to e to the power x, and we differentiate e to the power x with respect to x. Now we differentiate j with respect to sigma. Now, now sigma is dependent on, yes, because this is with respect to h out, right? Now let us see. We had h out here. Yeah, this was our h out. So how did we compute h out? Yeah, we did a lot of things. So our h out was, so what was our h out? H out was some other activation, say, let me say that the sigma activation is sigma 1. So sigma 1 and sigma are very different things. So this was sigma 1 of H2, right? So what should be the, so now what will be the rate of change of H out with respect to what? So what will come here? No, it will not be H2 because we're applying sigma 1 on top of H2. So actually this is A1 actually, or A2, I think I gave some name here. Yeah, I named it A1. So this is basically H out depends on A1. So this is basically A1. Now we go to A1. So A1 is, sorry, A1 is sigma 1 of H2. So A1 depends on H2, right? So this will be with respect to H2 and so on. So now we will be able to compute. So now if I want some derivative, say the derivative of z with respect to h2, so we can just put this computation here, and if you do this computation you will get h2, right? So whenever you are trying to make this update step of the gradient descent, you will need this gradient of the loss with respect to different quantities. Say you will need something like what is the rate of change of the loss with respect to W2. So then you have to go from, so this depends on your sigma, then your sigma depends on H2, and your H2 depends on W2, right? Because your H2 was W2 H1 plus we had no beta. So if you want to compute this, you need to compute this. If you want to compute this, you need to compute this, and so on, right? So now look at one thing. If I want to compute the rate of change of the loss with respect to W2, we need the rate of change with respect to sigma. So here also we need to compute the same thing. So instead of computing these things again and again, we will create some matrix, or we'll create some array and save all of these computations. And during this, you can just call the computations and do this whatever is can compute the required gradient that you want. So now we have your network, we have your input, we have your neural network where you do feed forward. You get some output, and from the true labels you get some loss, right? Using this loss, you can do back propagation algorithm to compute the gradient of the loss, right? And then once you do the gradient, compute the gradient, you can update the weights, update W1 and W2 using gradient descent. Then once you do this update again, you will do a feed forward. Once you do a feed forward, you will get a different loss. Hopefully this loss is less than the previous loss. Again, you will do gradient descent. So you will continue this process of feed forward and back propagation until you are satisfied with the loss. So once you are satisfied with the loss, so that means you have trained your neural network to whatever quality you want, and then you can use that model for say testing or validation. So this is the whole process of training a neural network using feed forward and back propagation algorithm. So is the whole process clear, or are there any doubts in here? Yeah, if you have any doubts, you can also speak up if you want. So if this process, because this is the most basic, uh, basic way, or the most or you can say the popular way of training a neural network. So anything new that will be taught in the class from now on, or any neural network that you implement, it will always follow this procedure. You will do a feed forward, you compute some loss, and then you can do a back propagation. Okay, I don't have a code ready with me, but you can always do that, right? So I will just give a very brief pseudocode type of thing, right? So, okay. So suppose I say this is my data set, and I have say uh, three data points, right? I have x1, I have x2, I have x3. I have 3 data points and I have their corresponding labels. I have y1, y2 and y3. So these are the two labels, right? And let me say that each x1, so let me say any xi belongs to say R2. That means each input is a two-dimensional. So if I plot it, so I have say xi1 and xi2. So I can plot it something like this. I can plot it on the two-dimensional plane on the R2 space. So that means xi will have xi1 and xi2. So is the data is it clear how the data looks like? And for simplicity, let us say that this is a regression problem. So it is a regression problem. So what is the size of y? What is the dimension of y? Yes, right. So y is your 3 cross 1 matrix. So this is a 3 cross 1 vector. So that is each y1 is a real number, right? So this is a real number. Now let me design a neural network for this. So now my input dimension is 2. So for the first layer, input layer, how many neurons do I have? No, I have 3 different data points, but each data point is two-dimensional. I have 3 points, but each point is two-dimensional. So what should be my input dimension? Because for each data point, I will pass. So suppose I have said that my first data point is no. So suppose I say that this is my data point. This is at say 1, 2. This is at 2, 2, and I'm just saying these are not correct. This is a 3, 4. So I have x1. X1 has say 1 and 2 as the input. So my input layer will contain one neuron for each dimension. So I have two dimensions, one dimension 1 and dimension 2. So the input neuron will contain two dimensions. So this is for xi dimension 1 and for the ith point dimension 2. Is this clear?
So there will be two input neurons.
There will be, because I'm saying that my data, each data point is two dimension. I have 3 data points. Okay, that is good. But each data point is two dimensional. So this is one data point. This is another data point. This is another data point. So 3 data points, but each data point has two dimensions. So when I'm giving as input, I'm considering the input for a single data point. So the single data point will have two dimensions, right? It will have a dimension 1 and dimension 2. So for the input layer, I will have to consider an input neuron for each dimension separately. So the
Okay,
dimension,
understood.
correct, right? So the dimension of points and the number of data points are different. There can be hundreds of points, but if you have each data point to be two-dimensional, so input neuron will have two neurons. That's clear, right?
Yes.
Okay, good. So now let us say that I have hidden layer 1, and suppose I want to give say 5 neurons in hidden layer 1, right? So I give 5 neurons, 1, 2, 3, 4, 5, right? Each one. So now we discussed before, we have 2 neurons here, we have 5 neurons here. What will be the size of this matrix? W1 is 5 cross 2, right? Good. So we will define, so when you are writing a code, so you will mostly, if you are doing a very basic code, you will use this NumPy library. You must be familiar with it. So I will define some W1 to be NumPy dot say random dot rand. So this will give us a matrix, and I want my matrix to be of size 5 by 2. And because these can be any values, right? This can be real values. I'll say that my data type is float. So this gives your this one. This is your weight matrix here, right? So now next, what is the next step after you get this thing? So you have X, you have W1. So now you will compute H1 which is W1 dotted with. So if I am writing this code in Python, I will write something like this: numpy dot dot W1 and X, right? So what is the next step? So next step is the activation, right? Because once we have the hidden dimensions, the next step from H you go to A, right? And suppose I say that, for example, I'm just taking the sigmoid activation in this case, or the logistic function, right? So I will define a logistic function in Python, define logistic. Here I will input some Z, and it will output what is the output? 1 divided by 1 plus numpy dot exponential to be minus Z. And now once I have H1, I will get A1 by calling this function logistic of H1. So is this part clear? Anyone have any doubts? So I'm explaining in terms of a Python code because that is the easiest code to write. You can write it in MATLAB or whatever language you're familiar with. Okay, right. So now we had H1, now we got A1, and now because I am saying it is a regression problem, suppose again I have another layer of 3 neurons and I have a W2. So suppose I want to define this W2 as numpy dot random dot rand. So what will be the size of W2? Right, good. So your size of W2 is 3 cross 5, and you have D type equal to float, right? Again, suppose I have one activation here So I will get h2 as numpy dot numpy dot w2 into what should I multiply it with? What should I write here? Yes, right. We'll have h1 here, right? Or no, not h1, a1. So you understand why it is a1, right? You had h1 at this point. We applied the logistic function and got the a1 at this point. So now this is going to the next layer. So here I will write a1. Is that clear? Fine. So yeah. So now we have h2. Suppose I use the logistic function again. So from h2 I need to get a2. So how will I get a2? What should I use to get a2? Yes. So we define this logistic function here. Yes, right. Activation of h2. We define this logistic function here. So now I will call this logistic function and then I pass h2 here. So now I get a2, right? So again, what is our size of a2? This 3 cross 1, right? With 3 neurons here, our size of a2 is 3 cross 1. Great. And now, because this is a regression problem, I will use only one output neuron. And suppose this is W3. So let us say this is W3. What will be the size of W3? One cross three, great. So we have this W3 here, and now your wipe rate, because yeah. So what is the activation function I need to use here? This is a regression problem. What will be the activation function here? We got something. We'll get this one H3. Okay, one. So the because this is a loss, this is a regression problem. We don't need any activation. You can just uh, multiply it with W3. So you do np dot W3 times. So what should I multiply it with? What should I multiply this with? right? I will multiply this with a2. So now I got the, yeah, right. Now I got y prep, right? Now what is the next step? We have to define the loss, right? We have to define the loss. So let me write a function of for loss. So I will name it MAC loss, and I will give some true labels, or let us say y, and our predicted labels. So my loss is uh, y minus y squared square, and you do a sum of it. So this is the MAC loss. So now I'll create a variable called loss. So this is basically, you call this function MAC loss, and you do y comma y spread of it, right? Now we computed the loss. So what was the next step? You do the feed forward, you computed the loss. What is the next step? Yes, we have to minimize this loss. So for minimizing the loss, this loss, we have to write the backprop algorithm, right? So this backpropagation algorithm will have the derivative of your loss with respect to everything. It will have derivative with respect to A2. It will have derivative of the loss with respect to H2, derivative of loss with respect to A1, derivative of loss with respect to H1, then derivative with respect to W3, W2, W1. So these all things are your variables. So you have to compute the derivative of your loss with respect to each of these variables. So for this, what you will do is you define a function. So I say define derivative of loss with respect to, say, A2, d loss dA2, and I input my loss here. And because I am doing a MAC of this, so what is your MAC? MAC is basically summation y minus y spread, right? Square. So what is the derivative of this with respect to x? This is simply summation y minus y spread, right? The derivative of this with respect to x is this, right? So here you will return 2 times sum y minus y spread. So this thing gives you this. So similarly, you will write a function for computing this, for computing this. So for this thing, you have to derive each of these equations by hand, derive each of these by hand, and write functions to compute these equations by hand, and write a function for each of these derivatives that you require. After that, so is this part clear? How to create these backprop functions? Yeah, great. So because it is a type of chain rule, so you will write. So I am showing it a very simple one. So for this, you need some time to derive. It is easy. You just have to derive it by hand and write the functions. So we don't have much time, so I won't show this. So now once we have these derivatives, we'll store all of these derivatives. Right? We'll store them somewhere. Suppose we have some we have some create some array of derivatives, and we'll store all of these things here to store all the derivatives. So now Now we'll put all of these things in a function. So first of all, I'll write a train function, right? So inside this train function, what I'll do, I will say I want to train for 500 iterations. So I in range 500. I'll train for 500 iterations. So given x, so suppose I define my model to be, so suppose I have a different function, say model. So what this model does is it puts all of these things inside the model. So you will define your W1 here, you have your W2, you have your W3, you will define your logistic function inside this model. So basically when I call model here, so suppose given some x, I will call this model function. It will give me ypred, which is the feed forward network or feed forward algorithm, right? Now using ypred, I will compute the loss using MSC loss, right? Then I get the gradients from these derivatives that I have, right? Now I will do the gradient descent update step. So we will have say W2 equal to W2 minus some eta times your gradients. You go to gradients and say, suppose you have a function of for d loss by dw2. So we call this function to get this. Similarly, you do this. Similarly, you do this. So you will update your w's in this step. So this is a gradient descent update step. And then you continue this process for 500 epochs, say 500 iterations. And once you have this, you'll get some model, right? It will return you the best weights that you have. What are the W1, W2, and W3 that you have? So once you have the new W1, W2, W3, now you can just use your testing data to test what is your, sorry, you use some test data to predict on your test data. So pass X test in this case. So this is the whole flow of the neural network training from feed forward to back propagation to testing. Are there any questions in this step? So in general, if you are using say PyTorch or TensorFlow, you don't have to write all of these functions. There is something called AutoGrad. I think it may be covered in the future classes. So this AutoGrad function computes these things internally. You don't have to write functions from this. So this is just for a simple example that I have shown. So if you use AutoGrad, you just have to define your model and just say model dot backward. It will do the backward propagation by itself in PyTorch or TensorFlow, and you just get back the outputs of your parameters of your model. So using those libraries, it is very easy to do all of these actions. Are there any doubts?
Thank you.
Okay, thank you. In MATLAB also there may be some, I have not used it, but I think in MATLAB also there are some neural network libraries. You can just call that package and we can just pass your data x and y, and it will compute the your gradients by itself. It also has some autograde capabilities. So they even have the loss function specified. So yes, this video will be uploaded to the YouTube channel. I think you can find this link in the Excel sheet that has been shared for the course, right? So we will find the link for this video there. Okay, thank you. I will upload these notes also in the shared sheet. You can find all these things there. So thank you for attending this session. We'll meet again next week. So we can leave the chat. Thank you. Yes, I will upload this video and the link will be shared in a few minutes. So you can check out the Excel sheet and access the link there.